Hello everyone and welcome to Jam Academy. The objective of this problem is to show you how to calculate the work done by a variable force. Now, this is a very applicable and beautiful problem. Most of us, including you maybe, have gone to the park, and one of the favorite activities in the park is swinging on a swing. I often take my kids to the park, and one of the things I love to do is to push them on a swing. They really love that. Now, to do this, usually a variable force, a horizontal force is applied. You pull. I usually pull my child, Audrey, and then I let go. What happens is that she swings back and forth. That forward and backward movement, we call that simple harmonic motion. But we will talk about that in another day. Now, we're going to make a couple of assumptions here that I pull Audrey gradually at a constant speed, which means that I'm pulling her slowly to a new height and then let go. Now let's suppose that her mass and that of the seed is m, and the length of the chain where she's hanging is L, and I push Audrey until the chain makes an angle theta with the vertical. We need to calculate the total work done on Audrey by all the forces. Now, what is the work done by the tension in the chain, as well as what is the work you do by exerting the force acting on Audrey? This is a very important question. Now, there are two ways that we can calculate the total force acting on a particular system. We can first calculate the net force acting on the system and then calculate the total work done by the net force. Let me say that again. There are two ways by which we can calculate the net force acting on an object or a system. We can first calculate the net force, then calculate the work done by the net force. That work done is the total work done on the system. This is actually the easier way to do it. Calculate the net force and then calculate the work done by the net force. That gives you the total work done on the system. Now, the second way, which is a little bit lengthier and sometimes more difficult, is to calculate the work done by the individual forces acting on the system, and then sum up all the work done by these forces to give the total work done on the system. Now, I prefer the first rather than the second. But since this involves forces, the very first thing we need to do is to draw a free body diagram. So what do we have here? We have his weight, which acts vertically downwards. This is mg. We have the tension in the chain. This tension is T, and we have the horizontal force F. Remember that the force is applied in such a way that the system moves with a constant speed. That means that the net force acting on the system is zero. And if the net force acting on the system is zero, it also implies that the total work done on the system or on Audrey is zero. That means that the total work done on Audrey by all the forces is zero. So the next question is, what is the work done by the tension in the string on Audrey? If you look critically on this, I'm going to draw a line here. You realize that at all times, the angle between the tension on the string and the direction in which Audrey is moving is 90 degrees. It's 90 degrees. And if the force is perpendicular to the direction in which, let me say that again, if the force is perpendicular to the direction of motion or to the direction of the point And if the force is perpendicular to the direction of displacement of the point of application of the force, then the work done by the force is 0. Let me say that again. Then the work done by the force is 0. That means that the work done by the tension on Audrey is definitely 0. I can show that to you pretty quickly. So let me translate my diagram right here. So we have the force F. We have the weight acting vertically downwards. And we have the tension in the string T. This is my x-axis and this is my y-axis. This angle right here is theta. One thing that you can see is we can resolve the tension acting on the chain into two components. You will have the horizontal component. This is T sine theta. You have the vertical component. This is T cosine of theta. Now the system is in equilibrium, which means that the sum of forces in any direction will be equal to 0. So that being said, we can see that the sum of forces along the x direction, this will be equal to F plus minus T sine theta. This is equal to 0. So we can see that F is equal to T, the sine of theta. I'm going to call this equation 1. Similarly, the sum of forces along the y direction, this will be equal to T cosine theta plus minus mg will be equal to 0. What this means is that mg is equal to T, the cosine of theta. Let's call this equation number 2. Now the beauty of these two equations is that if we divide equation 1 and equation 2, we are going to have F divided by mg. This will be equal to T sine theta divided by T cosine theta. Now the t's can cancel. Sine over cosine is tangent, so this implies that F is equal to mg, the tangent of theta. So this gives us the magnitude of the variable force that I apply to pull my daughter very slowly at constant speed to a new height at an angle theta with the vertical. So the last question really is, what is the force that I exert on my daughter? Sorry, what is the work that I do by exerting this force on my daughter? So to calculate the work done by a variable force, W is defined as the integral of F cosine theta dot dr, and we are integrating from Ri to Rf. This is the general definition to calculate the work done by a variable force. To translate it to this particular scenario, so the work done by F will be equal to the integral of F cosine theta multiplied by ds, where s is the distance moved by Audrey from point A to point B. And that distance is this arc length S. Now there is a beautiful relationship between the arc length and the radius of the circle. By definition, S, which is the arc length, is equal to r theta. This means that ds is equal to r d theta. And if that is true, then we have, if that is true, then the work done by f will be equal to the integral of f. What is f? F is mg, the tangent of theta, multiplied by cosine theta, multiplied by r d theta. And we are integrating from 0 to theta. Remember that tangent is sine divided by cosine. So this can be rewritten as the integral from 0 to theta of mg bracket sine theta divided by cosine theta multiplied by cosine theta r d theta. The cosines can cancel each other. This would mean that the work done by f is the integral from 0 to theta mgr sine theta d theta. Now, what is the integral of sine theta? The integral of sine theta is just cosine theta, so this is just mgr bracket cosine theta from 0 to theta. Now, it's negative cosine theta, from 0 to theta. This will be equal to mgr bracket 1 minus cosine theta. So this is the work done on Audrey by the force, the variable force F. This is a very beautiful result. So let's kind of analyze the results carefully. What happens if, so the question is, what happens when theta is 0 and what happens when theta is 90 degrees? When theta is 0, Audrey is at rest at the initial point A. But when theta is 90 degrees, Audrey is right up there. So let's analyze the two scenarios and see if it makes sense. So if theta is 0, cosine 0 is 1, that will mean that W will be equal to 0. So when theta is 0, no work is done on Audrey by the force, because there is literally no displacement. But when theta is equal to pi over 2, cosine of pi over 2 is equal to 0, in which case the work done will be equal to mgr. The work done will be equal to mgr. This is equivalent to the work done in lifting an object from the ground to a height of r above the ground by gravity. Thank you so much, fellas. If you have any question regarding this very beautiful problem, I would recommend that you ask your question in the discussion forum right below this video, and we will be able to help you. Thank you. This is Kimmel Honor, and you're welcome. Bye.